Hello everyone, in today's video we are going to discuss the second classification, that is collector to base bias circuit. So here we have got a circuit where the VCC is connected with the resistor collector, and previously we were collecting our resistor base and resistor collector parallelly. Now we are connecting it interconnected. See, resistor collector is connected with the resistor base. This base is not directly connected to VCC, it is interconnected, and we have IC value equals to beta into IB has a constant value. So here we have that resistor base is connected between transistor collector and the base terminals. That means this RB is connected between transistor collector, so this resistor collector, and base terminals. Okay. Next, this circuit has significantly improved bias stability for hybrid parameter of current gain changes compared to the base bias, where the voltage across the collector emitter is also dependent on the current on base and current on collector. From KVL we can find VCE equals to VBE plus IB into RB, that is current across the resistor base, where from which we can find the IB value as equals to voltage across collector emitter minus voltage across base emitter whole divided by resistor base. Any changes in VCE, there is also a change in current across the collector. Value of base current will change when the current across the collector will change. So here whenever there is a change in current in IB or IC, there is simultaneously effect to both. So IC equals to beta into IB, and IB plus IC equals to beta plus 1 into IB. So when the current is flowing from VCC to voltage across the base emitter, it will flow IC plus IB across the resistor collector. When the current is flowing from VCC to VCE, it will flow only the IC as a current. To simplify the process, on equation is derived by base current IB. Let us write KVL to outer loop. Which is our outer loop? So it is from VCC to VCE is our outer loop. So let us write a KVL to outer loop. So VCC equals to VCE plus current across the collector into current across the resistor collector. So here we will be having VCC equals to VCE plus IB plus IC into RC. So this is our current is flowing, and similarly when we apply for inside KVL loop, we'll get VCE equals to IB into RB plus VBE. So VCE minus VCE equals to IB into RB plus VBE. So where this VCC, so equating 1 and 2 we are getting. So equating this equation and this equation will get as IB into RB plus VBE plus VCC minus RC into IC plus IC into RC. So we are equating equation 1 and equation 2. Okay. So here we'll get, so VC will become 0. What left over? VB plus VC. When we send here, it will become VB minus VCC, where we get the collector current across the resistor base and collector current across the itself. So finally we get VCC minus VB equals to current across the resistor base. We take as the current common, has I into B has a common between RB and RC. So we'll get this as our final equation. Substituting IC, we know that this is a constant formula, IC equals to beta into IB. We'll get our value VCC minus VBE. So wherever IC is there, we have to replace it with beta into IB value. So our final equation, when we replace in equation 3, in this equation we replace IC value, will get as IB equals to VCC minus VBE whole divided by beta plus 1 into RC plus RB. Okay.